Hey, ChemGal here. Real quick, let's go ahead and solve this problem. What if your professor told you to draw the constitutional isomers for C5H12? Well, first we gotta know what's a constitutional isomer. And so two compounds are constitutional isomers if they have the same molecular formula but different connectivity. We might first start off by drawing a regular pentane chain, since pentane has 5 carbons. 1, 2, 3, 4, 5. And if we wanted to go ahead and draw that in condensed form, it might look like this. And so we see here that if we tally up all the hydrogens, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, we have a total of 12 hydrogens and 5 carbons. So this compound here has the molecular formula of C5H12. So now we have to draw another constitutional isomer for this compound. So this time we might draw a 4-carbon chain, and then we might place a methyl group here. And if we do that, we see that we have 5 carbons. And we can draw out the condensed form to see how many hydrogens this structure has. So now if we tally up all those hydrogens, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a total of 12 hydrogens here. Our molecular formula here is C5H12. And then we might try branching another way. We might draw a carbon chain of 3 carbons, and then 2 methyl groups attached to carbon number 2. And so if we draw out the condensed form, we see that it looks like this. And if we tally up all those hydrogens, we have 3, 6, 9, 12. And so our molecular formula for this structure has 1, 2, 3, 4, 5 carbons, C5, and 12 hydrogens. Each of these compounds have the same molecular formula of C5H12, but very different connectivity. And so that means that they are all constitutional isomers of each other. Another way your professor might ask you this question is by drawing out these structures and asking you what's the relationship between all of them. And so you can go ahead and label them constitutional isomers. So now you might be wondering, what if I draw a pentane chain and I place a double bond here between carbons 3 and 4? Does that have the same molecular formula as C5H12? We could take a look at the condensed form to figure it out. And so if we tally up all the hydrogens in the condensed form, we see that we have 3, 4, 5, 6, 7, 8, 9, 10. The molecular formula for this structure is C5H10. Why is this C5H12 and this C5H10? Where did those 2 hydrogens go? So now we can recognize that in forming this second bond here, these 2 carbons had to lose a hydrogen. Where they were once CH2CH2, now they're CHCH. So we call this a unit of unsaturation. Let's go ahead and talk a little bit more about these 2 structures here. So now I have redrawn for you these 2 structures. And you know that when a structure has all single bonds, we call this an alkane. And when a structure has a double bond in it, we call it an alkene. And so we see that over here, we follow the chemical formula of C5H12, whereas here we had C5H10. We have special chemical formulas for alkanes and alkenes. So for an alkane, the chemical formula is going to be CnH2n plus 2. As for an alkene, it is CnH2n. It makes sense because if we have 5 carbons and we plug that value in for n, we're going to get C5H2 times 5 plus 2, which is going to be C5H10 plus 2, and that makes for a total of C5H12, which follows this molecular formula here. And if we plug in 5 for n here, since we have 5 carbons, we see that we're going to have C5H2 times 5, which is going to be C5H10, which follows this alkene formula here. And you might be wondering, why do we care about all of this? And that's because if your professor tells you to draw the constitutional isomers and gives you a molecular formula, you can now find out if that formula belongs to an alkane or an alkene. And so remember that I said that when you have an alkene, such as in this case, if you have one double bond, we say that that is a unit of unsaturation. And so because we have no double bonds here, we would say that this compound is fully saturated. So to recap, when you have all single bonds, you are saturated. But if you have a double bond, you have unsaturation. And so we compensated 2 hydrogens to form that double bond. So there's another reason why we might compensate 2 hydrogens, and that's also when forming rings. So for instance, if I were to draw a ring here, this ring would have a molecular formula of C5H10. And that's because it lost 2 hydrogens when connecting 2 of those carbons. If we draw out the condensed form, we're going to have CH2, 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 CH2. And so we have 2, 4, 6, 8, 10 hydrogens here. So we lose a pair of hydrogens when forming a ring as well. And this is also considered a unit of unsaturation. So if you ever find that you have a molecular formula falling under CnH2n, you could have an alkene or a ring. Knowing this, we can try to draw the constitutional isomers for C4H8. So let's first establish whether or not this is going to be an alkane or an alkene. So if we draw out the molecular formulas for those, we know that an alkane has the formula CnH10 plus 2, and an alkene has the formula CnH2n. So we know that N is going to be the amount of carbons we have. We have here 4 carbons. N equals 4. And if we plug in 4 for each of these formulas here, we're going to have C4H 2 times 4 plus 2. And so that's going to give us C4H10. And over here, we're going to get the formula C4H 2 times 4. And so that's going to give us C4H8. And so our formula is going to follow the formula of an alkene. So we know that we're working with an alkene over here. So now let's go ahead and erase this and draw out all the possible alkene structures we can have for this molecular formula. So you might first start off with your basic butene chain, and maybe you'll place the double bond between carbons 1 and 2. And then you might draw another butene structure, but this time you'll place the double bond between carbons 2 and 3. So then you might be thinking, I can draw another constitutional isomer if I place my double bond between carbons 3 and 4. But why wouldn't this be another constitutional isomer? Take a moment to think about why this structure would not be another valid structure. And that's because this structure over here is exactly the same as this structure, just turned around. Remember that when we name alkenes that don't have any functional groups, we name by giving the double bond the lowest set of numbers. So we would number the structure 1, 2, 3, 4. And so technically this double bond is between carbons 1 and 2, just like this alkene over here. Therefore, these two are the same structures, just turned around, and so this would not be another valid structure. So now we might try branching a little bit. We might draw a propene chain and place a double bond between two of these carbons. So now this would actually be the same structure as placing the double bond over here or even over here. So it doesn't matter where we place the double bond because essentially it would be the same structure. And so if we go ahead and look at these in condensed form, they might look like this. Each of these structures have the correct amount of carbons and hydrogens. These structures here are all C4H8, meaning they have the same molecular formula. But now, what if your professor changed this question up a little bit and told you, draw at least 4 constitutional isomers? You would have to come up with another constitutional isomer. And so remember we said that this molecular formula over here follows the formula of CnH2n, which means we can have an alkene or we can have a ring. Because remember that a ring also uses 1 unit of unsaturation. So if we wanted to, we can arrange this structure in the form of a ring. And this over here is called cyclobutane because it's butane in a cyclic form. And if we look at this in condensed form, it would look like this. And so we see here that we have 1, 2, 3, 4 carbons, and we have 2, 4, 6, 8 hydrogens. With that one ring closure, we form 1 unit of unsaturation. And so that's going to allow us to have the correct amount of hydrogens. Each of these compounds have the same molecular formula, but very different connectivity. They are all constitutional isomers of each other. Now I want you to take a moment to try this one on your own. So first we got to figure out whether or not we have an alkene or an alkane. We see that this molecular formula over here follows the formula of an alkane. This means that we can only have single bonds in the structures we're about to draw. You might have started off by drawing a classic propane chain. And if we drew the expanded formula for that, we have 3, 4, 5, 6, 7, 8 hydrogens. So we follow the correct formula of C3H8. And so now this is really cool because this is the only constitutional isomer that you could possibly form for this molecular formula. So now I want you to take a moment to draw all the constitutional isomers for C4H10. First, we got to figure out whether or not this is the formula for an alkane or an alkene. We find that we have the chemical formula for an alkane. We can only draw structures that have single bonds. And so you might have started off by drawing a butane chain. And then you might have tried drawing a propane chain and placing a methyl group on carbon number 2. There's no other structure that you could have possibly formed here. Therefore, these are the only 2 possible structures that you could have formed as constitutional isomers for C4H10. Draw at least 6 constitutional isomers for C5H10. And so now you know we got to figure out whether or not this is an alkane or an alkene. We see here that this formula is going to follow the format of an alkene, C5H10. So all our structures here must have at least 1 unit of unsaturation, either by being an alkene or having a ring closure. You might have started off and found the following structures. You might have accidentally formed a duplicate by putting the double bond over here. Now I want you to go ahead and tell me, why is this not a valid structure? This is not a valid structure Because if we, let's say, turn this structure around so that it's angled in the position of the double bond with this structure over here, and if we rotated that single bond here so that it's downwards, we would see that we formed exactly the same structure that we have here. We see that this double bond here is attached to an ethyl group and a methyl group, a methyl group and an ethyl group. And so these two structures are exactly the same. So whether or not we draw the bonds like this or like this, it doesn't matter because those are single bonds that can rotate. When we rotate this structure, we see that it is exactly the same as the one beside it. And so this is not another valid structure. This is only 5 structures here, and the problem asked you for 6. So you might draw the last structure as a ring closure for pentane. Will actually have the same molecular formula of C5H10 because it also has 1 unit of unsaturation, just like the alkenes here. Now you formed successfully 6 constitutional isomers for C5H10.
So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!